specifying DSPN itself, which we should do, but it's not as interesting. And then there's the implications of this kind of architecture. More verification, and we can actually pick up here the details of DSPN once the talk goes on.
Focus. Thanks. Do folks want to move forward a little bit cozier? You can do it. So, quick announcement, our next discussion section has been permanently moved from being between 9 to 10 a.m. to 1 to 2 p.m. Same day, but so you have more later hour options. Thanks. Okay, so topic for today, we're going to start with a new topic altogether. We're done with intra-domain routing. Our topic is still routing, but in the context of interdomain, what we call interdomain routing, or routing across domains. And so far, all of the lectures you've seen with Murphy lecturing, we talked about routing on a graph that looked like this, made up of routers and links and end hosts. And if you remember, Murphy made the point that this is how we tend to do routing within a single domain. Okay? And so from now on, we're going to focus on kind of this notion of a domain, or more formally what we'd call an autonomous system. And I'm going to define that in a second. And we're not going to worry so much about the details of how routers and links are interconnected within this domain. Okay? Instead, we're going to focus on the domain as a logical node, so think of it as one node. Okay? And I'm going to represent it with clouds, just like we had squares for routers and circles for end hosts. And more generally, we're going to focus on what we call this interdomain topology, or the AS graph, the autonomous system graph. So this is kind of the end-to-end view on the internet of how different networks or different domains are interconnected. Okay? Specifically, we're going to focus on this question of how do I find a path across this AS graph. So we're finally in the realm of doing an end-to-end path across the internet, across multiple ISPs. And at the same time, we shouldn't forget that actually that path is not going through clouds. It's going through a series of links and routers that are within each of these domains. But for the most part, we're not going to talk about that in this lecture. In the next lecture, we'll get back to talking about how intra-domain and interdomain actually intersect, how they integrate. But for today, we're going to stick with this picture of I have a graph that's made up of these clouds or ASs that are interconnected. And I'd like to start by just taking a closer look at one of these domains or autonomous systems, and what is it exactly, and what is so special about the interdomain topology and autonomous systems. And so autonomous systems, I'll be using the term domain and AS interchangeably. Autonomous system is a slightly more formal term for what we've been calling a domain informally. And an autonomous system is simply a network that is under the administrative control of one entity. So UC Berkeley is an autonomous system because the UC Berkeley staff decide how to operate our network. AT&T is another AS. France Telecom, Deutsche Telekom, there are many autonomous systems or ASs across the internet. Okay? And as I said, informally, we're going to call them domains. What defines or what makes a network an autonomous system is the fact that it has been assigned a unique autonomous system number, or ASN. This is a number that's assigned by this organization called ICANN. I think Murphy talked about it in the context of assigning IP addresses. So if you want to be an AS, you have to go to ICANN, you have to make your case, and you get an autonomous system number. Berkeley, for example, is ASN number 25. Fun fact, this is John Postel. He was one of the early internet pioneers, really influential in the design of TCP/IP. And actually, in this context, until his death, he was a single person that handed out ASN numbers for the entire internet. So we had one person doing all ASN management for the entire internet. This is now, of course, this organization ICANN with lots of international laws and so on. But way back, there was this one guy handling it. Just if you're curious, how many AS ASs do we have on the internet? This is going up to 2020. I believe this number is close to 100,000 now. So that kind of tells you the scale of the AS graph. It's about 10,000 nodes. If you're curious where they go, as you can see, the US is hogging the largest number of autonomous systems. This is not surprising. Brazil is number 2, which was somewhat surprising to me. But in general, you see these handed out across the world. Okay. From our perspective, as we talk about autonomous systems, there are kind of 2 common kinds of ASs that we're going to talk about and that are important for how we do routing. The first is what we call a stub AS. This is an AS it only exists and its only job is to provide connectivity to its directly connected users or hosts. So it's not in the business of carrying traffic between other ASs. It only exists to carry traffic to and from its directly attached host. So UC Berkeley is an autonomous stub AS. Typically, you'll find that enterprises, businesses, people that are not in the business of providing network connectivity, that's not why they exist. Those tend to be stub ASs, enterprises, and so on. Okay? The other kind are what we call transit ASs. These are ASs that will carry traffic on behalf of other ASs. So these are the ASs you'd expect, AT&T, Verizon, and so on. They're kind of in the business of internet connectivity. That's their reason for existence. And in practice, we'll get to this a little bit more in slides going forward, but in practice, there's quite a bit of variance in the nature of transit ASs. So you might have a transit AS, for example, that covers California. And then you might have a transit AS, what we call tier 1 ASs, that cover the entire globe. Okay, so there's a little bit of hierarchy even amongst transit ASs. But by and large, this is an important distinction. Stub AS is only for your directly attached users. Transit ASs, you carry traffic for other ASs. Okay. So I want to talk a little bit more about that interdomain topology and what makes it unique. What makes it so different from all the graphs and topologies you've been thinking about so far is that the topology is shaped by business relationships between the ASs. So now when I say that on the AS graph, A and B are neighbors, it means they have a physical connection, just like 2 routers that had a link between them. That is still true. But it also crucially means that they have a business relationship, by which I mean they have a legal contract that defines what service they're providing to each other and how they interact. And that really determines why we have the topology we have. And so there are 3 basic kinds of these business relationships on the internet. If I take 2 ASs, X and Y, the relationships they can have with each other is you can either be a customer of another AS, or you can be a provider to another AS, or the 2 ASs could be peers. Okay? And so what does that mean? The business implication is if you're a customer, then you're paying your provider. So customers always pay providers, and peers don't pay each other. They exchange traffic, but they don't pay each other for that exchange. So as an example, you can think of Berkeley signing up with AT&T in order to connect to the rest of the internet. Berkeley would be AT&T's customer, and AT&T would be Berkeley's provider. Okay? Why do ASs peer? We'll get to that in a minute. But typically the assumption underlying why 2 ASs are peers, the reason it makes sense for them to be peers is they're kind of the same size or scale, and that they exchange roughly equivalent amounts of traffic. And this is all codified in the contracts that they sign with each other. There'll be something that says, for example, that over a month, the 90th percentile of traffic that I sent you is within 10% of the 90th percentile of traffic that you sent me. So there's some technical definition of equal traffic that's in a contract, and that's kind of how we decide that we're meeting the condition to be peers. Okay? And so let's talk a little bit now about how these affect topology. Any questions on this so far? It's pretty intuitive, I think. Okay, so we're going to look at a lot of these AS graphs. So let me walk through this a little slowly so you kind of internalize in your head what's going on here. So this is a topology with 5 ASs, A to E. And I'm showing you here the relationship between these ASs, where I have this directed arrow for provider-customer. And so you can see in this graph, we have a bunch of provider-customer relationships. And then I have a different arrow edge, which I don't have any in this right now, but we would be using this other type of edge to denote a peering relationship between two ASs. And just to put it up there so you have it, remember customers pay providers and peers don't pay each other. Okay, so in this example, D is a customer of B, B is a provider to D, but at the same time, B is a customer of A. A does not have any providers, it has multiple customers. Okay? You could map this to D could be Berkeley, B could be a regional California ISP, A could be a global AT&T. So if I looked at this graph, I would say that D and E are stub ASs. Right? They don't have any customer ASs. And A, B, and C are transit ASs. Okay? Because they're carrying, for example, B is carrying traffic between D and A. A is carrying traffic between B and C. And in general, when we draw these graphs, we're going to draw stub ASs at the bottom and increasingly larger transit ASs at the top. So there's kind of this hierarchy. Yeah. Yeah, and so in fact, inside, if you look inside AT&T, they have portions of their network where they have directly attached hosts and directly attached customers, but they're also providing transit. And so typically we would call those transit, but they are playing the role of both. Not necessarily, no. Okay, so on this figure here, I'm going to say that I think it would be a great idea for B and C to have a peering link or to have a peering relationship. Anyone agree with me? Anyone want to say why? Yeah. Exactly. So let's say D and E talked a lot, right? And that traffic has to go BAC. Both B and C have to pay A to carry that traffic. So at some point, they're going to look at their traffic and say, this is quite expensive. If we just directly peered, we would actually save money on both sides. Both B and C win by putting in that peering link. Okay, so this is why we have peering relationships. It saves money for some of these transit ASs. Any questions on that? Okay, so moving forward, let's go back to this kind of AS graph. In practice, you wouldn't have an AS graph that looks exactly like what I have up here. Instead, you would have one that looks more complicated like this, where you have a large number of these ASs at the top. And the reason is largely for geopolitical reasons. Right? Nobody wants to have this one global AS that is an American company or an Asian company. Every country wants to know that they have some set of options, that they're not dependent on one single administrative entity. So we tend to have a large number of these ASs on the top, and all of these ASs on the top will peer with each other. So these are ASs we call tier 1 ASs. They're the very top of the hierarchy. So what defines a tier 1 AS is it does not have a provider, and it peers with all other tier 1 ASs. Beyond that, there's a little bit of kind of informal notion of what makes you a tier 1 AS. Typically, if you look at the characteristics, these two things always hold. You don't have a provider, which means that you never pay anyone to carry traffic for you, and you peer with all the other tier 1 ASs. And sort of informally, if you look at them, they tend to be across at more than one continent. So you typically not have a tier 1 AS that is in only one continent. And they tend to own these kinds of transoceanic links that go, transatlantic links, transpacific links. These are very expensive. They take care to manage. So the point at which you own and operate those links, you've kind of graduated to be a tier 1 AS. Examples, you'd probably heard of them. AT&T and Verizon are obviously the US ones we all know. In Europe, British Telecom, Deutsche Telekom. In Asia, Singtel, NTT. Those are some of the ASs that people would consider tier 1. Okay. This is kind of the context now that we've set up for interdomain routing. Everything is going to be, we're going to talk about how we select paths and routes, is going to be in the context of this kind of setup, this ecosystem of ASs and business relationships. So any questions before I move on? Yeah? None necessarily. We use the term interchangeably. You can be an ISP without, okay, this is in the weeds of the details, so don't worry about it from an exam perspective, but you can be an ISP without being an autonomous system. So you could, for example, say that you're in a rural part of California where there is no connectivity, and so you're going to be an ISP in the sense that you go set up infrastructure, and you provide connectivity to the people in that area. But actually, you just get a prefix from AT&T. You don't have your own autonomous system number. So that's a little bit just, differences in the practice. But the way we'll be using it, ISP and AS, you can think of them as equivalent. Yeah. Yeah. So all the tier 1 ASs will connect to each other in a full mesh, typically. Any other questions on this? Yeah? Yeah. That's the red link on top. Yeah. Yes, a lot, all the time. So as a tier 1 AS, certainly you would like it if these lower level ASs don't peer and they send all the traffic through you. They can't stop you from doing it. Right? Every AS acts independently in making those business relationships. So you can't block people from peering. Yeah. That's an interesting question. The question is, would you call someone like Google or an AWS a tier 1 AS? They have the footprint and the scale of a tier 1 AS, so they have the global networks, they have the transatlantic links. Typically, we don't because these cloud providers don't provide transit, meaning you go through Google's network if you're going to Google or from Google. But Google will not carry traffic typically to go between AWS and Azure, for example. And you can do it on top, but that's not a service they sell. So you can't sign up with Google the way you do with AT&T. And there's no technical reason they couldn't do it. It's just not the business they're in yet, at least. Any other questions? Okay. So where we're going to go from here now is if you have this ecosystem in your heads, we're going to start to design what that interdomain routing should look like. Again, anytime we talk about we're going to design something, we have to start with what are our goals. Right? So what are the goals for interdomain routing? In the context of intra-domain routing, we had these very clear goals. We said we want valid routes and we want least cost routes. Right? No loops, no dead ends, and least cost. In the context of interdomain, we still want all of those things. We still want valid routes. You never want a route that loops. That's just not a good idea. But we have two additional goals. Any thoughts? Yep. Okay, so stay within your system. I'm going to say that yes. Yep. Reduce cost. Anything else? Yeah, so that is the big one, though. I'm going to call it what we call as policy. Okay, so the two goals, one is scalability, because now we are talking about routing at internet scale. Right? This is not routing within a single domain. We are literally talking about all the billions of hosts on the internet. That's the job of interdomain routing. But the second goal is, what all of you were getting at, which is what I'm going to call policy, but it's a slightly loosey-goosey term at this point. We'll make it more concrete a few slides from now. But think of it as meeting the business goals of the operator, which could be mostly to save money or to make money. Okay? So let's get to scaling, and I'm going to go through this a little fast because I think Murphy touched on it a fair bit. Yep. Question? We'll get to that. Hold that thought in just a minute. Where you're absolutely right. Different countries will want to run their networks in their own way. I'm going to say that they want to have their own policies, and we'll talk about how they get to do that in just a few slides. Okay, so let's talk about scaling first. Right? What is the scaling challenge? It's simply that if I'm a router on the internet, give me any destination, and I have to know how to forward. I have to know how to find that next hop and send the packet on its way. Naive solution, we've talked about this. You could have an entry for every one of the 2 to the 32 IP addresses. Clearly, that would not scale, and Murphy went over this. And so Murphy, in his last lecture, said the key to scaling is how we do host addressing. And also said the way we do host addressing, if there's one word you should remember about IP addressing, it's hierarchical. It's hierarchical in the format, in the structure of the address. It's hierarchical in how we allocate the addresses. And finally, it's hierarchical. We're going to talk, Murphy's touched on those first 2 points. The last point is what I'm going to try and elaborate on today, which is how that hierarchy leads to routing scalability. Okay? So just a quick recap from Murphy's lecture. Remember, IP address is 32 bits. You can divide them into a network prefix and a host suffix. And the way allocation, or the way we hand out addresses, all the hosts in a network will share the same prefix. Okay. The important thing here is I can represent all the hosts in that network by just their prefix. And he also talked about how we have this dotted quad notation, where I'm going to have something like a /23 to tell you what the prefix in this address is. For my convenience, in this lecture, I'm going to use a.b/16 rather than trying to read out numbers. Otherwise, I always read them out wrong. But this is, again, the structure, the hierarchical structure of an IP address. Any questions on this? Okay, great. So what is key for interdomain routing is you have to realize that destinations in interdomain routing, they are now prefixes. Right? So in all the routing we've talked about so far, distance vector, link state, a destination was the host address, the full host address. In interdomain routing, our destination is going to be a prefix, which represents all the hosts in that network. Okay, and why does this lead to scalability? It should be pretty clear. If you look at a topology like this, and we said LBL had a /16, x.y, and UCB had a /16 of p.q, and they're both customers of AT&T. Well, if you go look at a routing table in Verizon's network, it just has to have 2 entries, one for each prefix. Okay? This is already a massive improvement. We've basically aggregated all of those hosts. You could have had 2 to the 16 hosts in LBL and 2 to the 16 in UCB. Instead of enumerating all of them, I just have to store 2 prefixes. Okay, this also tells you how interdomain routing, how we're making this scale. The prefix is going to get you to the final domain, to Berkeley or to LBL. And then only within that domain, you're going to worry about getting to the exact host. Right? Does this make sense to everyone? Okay. The second aspect of why hierarchical addressing helps is that the allocation is hierarchical. Again, Murphy had this slide where he said address assignment, you get from ICANN, gives out prefixes to regional registries that give it out to organizations like AT&T, that then you keep subdividing your prefix space as you allocate it. Okay. Look familiar? Why does this help me? Going back to the example we had, here I could have said, well, AT&T could have said, LBL and Berkeley are both my customers. Instead of giving them these completely disjoint prefixes, I have this address space that's /8, a dot something. I'm going to go and hand out a.b to LBL, and Berkeley gets an a.c. And so what happens to Verizon's table, it now just has to store one entry that says, if you're a dot anything, just go to AT&T. Okay. So there's 2 slightly different forms of aggregation that have happened. The first one was just saying I'm aggregating all the host addresses into one prefix. And now I'm saying I'm going to actually aggregate prefixes into shorter prefixes. Okay? And so we're getting kind of this benefit from exploiting hierarchical addressing. There's another benefit to hierarchical allocation and addressing. So let's say I had UCSF came along and is given the prefix a.d. What changes at Verizon? Does anything change? No. Right? It's a local change within AT&T's network. Verizon doesn't even need to know about it. So you get all this, yet another level of scalability. You don't send updates when you don't need to. So we like hierarchical allocation because of that. Hierarchical allocation addressing enables aggregation. Okay? So learn that lesson in your head. It's not perfect, though, and the reason it isn't is because ultimately, in order to get aggregation, hierarchy in addresses has to match the hierarchy in the topology. Okay? What do I mean by that? Let's go back to this picture here. And we've done beautiful hierarchical allocation and hierarchical addressing in this example. It matched the topology we had. Now let's say that LBL feels like they don't want to be dependent on just one provider. They really can't afford any kind of outage. So they say, I'm also going to sign up with Verizon as my provider. So I'm going to have 2 providers. This is something we call multi-homing. It happens all the time. Any AS or enterprise that is very sensitive to having outages might multi-home. They will go to multiple providers and say, I'm signing up with both of you for connectivity. What happens to Verizon's forwarding table in this case? Yeah. If I did nothing, I would just send my traffic to AT&T, which means my red link is going unused, which never makes sense, right? LBL paid for that link. They want it used. What would Verizon have to do? They would have to change their forwarding entries to make this work. Yeah, exactly. You would have to add yet another entry that says if you're going specifically to A.B, then you need to go over this red link. Anything else that has the prefix A, you go to AT&T. And when we talk about IP routers, we're going to talk about how we implement this prefix matching. We call it longest prefix matching to decide which of the two links you should go out on. Okay. So, but the thing to note here is that when we do multi-homing, it limits the efficiency of aggregation. And that's because we're breaking this assumption that hierarchical address allocation maps onto a topology. Right, so IP addressing and why we get scalability. Aggregation is what gives us routing scalability. But at the same time, the problem is aggregation can be broken by multi-homing. Okay, where multi-homing again means you've connected to more than one provider. And so where we end up at typically is kind of just how the two factors play out. So on the internet, you will see some providers that worry a lot about multi-homing making their tables larger. In certain parts of the network, there isn't much multi-homing, so you get very nice aggregation and scalability. But there's no solution, per se, to multi-homing. It exists, and it causes us some scaling challenges. In here? Yeah, great question. Should we have given LBL two different prefixes? We could have, right? That's your question. And one, you advertise one prefix to Verizon, another one to AT&T. You totally could. You're losing something there. What is it? The thing you're losing is that for any given address, you don't have the redundancy then. So let's say LBL had A.B and also had P.Q. If I now have a server that was given the IP address A.B. something, if AT&T goes down, you can't reach that server, even though I have Verizon as a provider. You could then do tricks later on to say, I'm going to give this server two addresses, and I'm going to go, when we talk about the DNS, we can talk about then, you can have the name lbl.gov mapped to two IP addresses, but that's kind of solving that problem at a higher level. Does that make sense to everyone? So recapping scaling, a router must be able to reach any destination. We don't like the naive approach of enumerating all destinations. And so instead we have hierarchical addressing, where you have an entry for a range of addresses. Hierarchical addressing is key to scaling. We talk about scalable routing, it's really the addressing that's making the routing scalable. So the key to why the internet is scalable has more to do with addressing than with routing per se. Any questions before we move on to policy? Okay, so let's talk about, we said the goal for interdomain routing was to enforce policy, to allow operators, AS operators, to enforce policy. Policy is a sort of nebulous term, so what do I mean exactly by policy? What we're going to see is that a policy is an administrator's preference for what kind of paths they like to see on the internet. And the AS wants their freedom to pick their route based on policy. Going back to an earlier comment, every AS has their own notion of what policies they want to implement. And just to get to it, what do I mean by policy? An AS, examples of AS policies would be things like, I don't want to carry this traffic coming from this AS through my network. That's a policy. And maybe it's your competitor, maybe you don't like the customers they serve, maybe you don't like the content. It's really whatever reason, no one cares what your reason is, that's your policy. You don't want to carry that AS's traffic. Different policy could be, I would prefer it if my traffic could be carried by AS number 10 instead of AS number 4. That's a preference over which ASs I would like to route through. Or under no circumstance, do I want to go through AS 54? Or whenever possible, I would like to not go through AS54. Those are all examples of policies. In the internet context and in interdomain routing, we say you can implement whatever policy you want, that we do not constrain the policies that ASs implement. So you could imagine a crazy policy when AS says, on Mondays I want to route this way, on Tuesdays I want to route that way. That should be doable in an interdomain routing solution. Okay. The thing to take away is none of this has to do with least cost paths. We're not talking about having one global metric and we want a least cost path based on that metric. That's just not what's driving route selection. Right, so if I said, oh, everyone can do anything, it sounds like the Wild West, how do we ever make progress? We do talk about typical policies. Like, what are the typical policies that all ASs want to implement? And frankly, they make a lot of sense. They're just common sense that this is what ASs want to do. And they're basically two principles for typical policies. Okay, so if I'm an AS and I'm in the business of moving traffic around, the policies or the principles that would make sense to me come down to money. And the first one is that if you're an AS, you shouldn't accept, or you typically don't accept to carry traffic if you're not being paid. Why would I be investing in all that bandwidth and carrying traffic if no one's paying me for it? Does that make sense? So what that means really is if you go back to those business relationships of customer, provider, and peers, the only reason I would carry traffic is if it's going to or coming from a customer. Okay? One end of that traffic has to be to a customer, otherwise I'm not getting paid. Okay? So my principle that drives my policies is I'm not going to carry traffic unless I get paid, which means I'm only going to carry traffic if it comes from or goes to a customer. The second one is that when I send traffic, so the first principle was about when somebody sends me traffic and asks me to carry it, when am I going to say yes? The second one is when I choose to send traffic to someone else. In deciding where I send my traffic, I want to either make money or I want to save money. Okay. What this means in turn is I'm always going to prefer, ideally I would like to send traffic to a customer because they pay me for it. But if I can't send it to a customer, I'm going to prefer to send it to a peer, because at least that's free. And my last resort, the thing I will do only when I have no other choice, is I will send it to a provider. And again, this is all about where you send traffic. There was a question somewhere? No. Okay. Does that? Yeah. That comes from or goes to a customer. So if, we're going to get to that in a minute, but the answer is, if the traffic came to me from a peer, right, I would look at that traffic and I would say, should I carry it? The answer would depend on where it's going. If it's going to a customer, then I would carry it, because my customer is going to pay for it. So what the implications of these policies are is kind of interesting, because what it tells us is, if you look at the AS graph, not all paths on the AS graph are valid. Just because I have a connected graph with edges doesn't mean all paths are valid. Instead, the paths that are valid, we say routing follows the money. A path is valid if it makes sense in terms of how money flows along that path. Okay? So let's look at this example. If I said here are two paths, these two blue paths, do you think this is a valid path from an interdomain perspective when I think about these principles of how money flows? Do we like this path? Yeah, right? Let's look at it, for example, from the perspective of A. Right? A is getting paid by D to carry that traffic, so it makes sense. A is not getting paid by B. It's carrying traffic between D and B, but that's fine because it's getting paid by D. The same is true for B. You could say, well, D is paying, but D has no choice. Right? It's a stub AS. It has to pay its provider to carry traffic. So when we talked about when I send traffic, I first try a customer link, well, D has no customers. Then I try a peer link, well, D has no peers. So then I fall back to a provider link, D has a provider, so it's sending it to A. Yeah, so why in practice do we have these queues on top, right? Like this AS at the very top. In this example, there's probably no good reason why you would want to have queue, but in general, the reason is because a smaller AS cannot peer with every other AS in the world. That's just, if you have an AS that covers, let's say, California, if that AS had to single-handedly connect you to every other AS in the world without one of these tier 1 ASs, they would have to have relationships with every AS in Africa, in Europe, in Asia, which that's just not what their business is, right? That's a physical link. So instead they say, I'm just going to go to AT&T, and AT&T has figured that out. Right. So the stub ASs here, typically the principle we are invoking, you could say, is where do I send traffic? And you try, you don't have customers, you don't have peers, so you send it to the provider. So it's kind of like a redundant application of the principle. It doesn't violate it. It's just not very interesting. What do we think about this purple path? Is this a valid one? Does routing follow the money here? Yeah, so everyone's saying no, right? And you see this by looking at ASB. ASB is carrying traffic between A to C, doesn't get paid by A, doesn't get paid by C. So why would you ever do that? Not a great idea, right? So traffic not allowed. This is pointing at a more general rule that ASs will provide transit between their customers. You're not going to provide transit where there isn't a customer on one end. And peers are not going to provide transit between other peers. So you're not going to have an AS that is taking traffic from one peer and sending it to another peer. Why would you do that? What do we think about this part? Even worse, right? B is not getting paid by A and then is getting charged by Q. This would be a sneaky thing for A to try to do. They've tried. You do. If you set up your BGP policies correctly, you would not be doing this. So this points again to a more general rule that an AS will only carry traffic to or from its customers over a peering link. I'm never going to take traffic from a peer and send it to my provider. What about this one? Yeah, bad to worse, right? In this case, F is getting charged by A and charged by C. This is effective. This is like AT&T sending their traffic to Berkeley and saying, hey, can you route it to Verizon? And then Berkeley gets charged twice. So we call this property, and we'll get back to it later, that routes are valley-free. You never go down the graph to a customer and then go back up. It just doesn't make sense. Okay, so hopefully now when we talk about that administrative preferences or policy shape interdomain routing, I hope you understand what that means. Yeah? The key thing here now, we want ASs to have the freedom to pick these routes based on their policy. They have to be able to do this with two properties. One is autonomy, and the other one is privacy. So let's talk about what those mean. When I say ASs want autonomy, what I mean by that is that every AS should be able or have the freedom to pick its own policies. And it should be able to implement that policy without coordinating with any other AS. Okay. So if I want to do Monday this way, Tuesday that way, I get to decide that, and I don't have to ask my other ASs to cooperate. That's autonomy. I also want privacy as an AS. So ASs are very sensitive to things like telling the world about what their business relationships are. Sometimes they don't even like to talk about who their peers are or who their customers are. They certainly don't want to tell everyone what their policies are. And I have this sort of explicitly, they don't want to explicitly announce these choices to others. Why am I kind of saying explicitly? A bit of a weasel word there. Yep. Yeah, because when you make a policy, it determines how your traffic flows. So the impact of those policies is kind of visible if you look at how traffic flows on the internet. So you could kind of try to reverse engineer what business relationships exist and what policies different ASs are implementing by sending enough traffic and observing from different vantage points and trying to reverse engineer. And there are companies that do this, and a lot of research papers try to do this to understand what ASs are doing. But they don't want to have to explicitly announce their policies. And a thing to note here, policy is what we're trying to achieve. Right? Implementing these policies is the goal of interdomain routing. Doing it while respecting autonomy and privacy, these are requirements on how we do it. Yeah? Okay, so in short, to recap, the AS topology reflects business relationships between ASs. Those business relationships, in turn, impact what routes we consider acceptable. And so interdomain routing, when we design an interdomain routing solution, we have to the goal is to make sure we can support those policy choices in a way that respects autonomy and privacy. Yeah. And so BGP, or the Border Gateway Protocol, is the protocol on the internet that does interdomain routing. That's what we're going to be studying. It is certainly not the only way to implement interdomain routing, but it's stood the test of time. It is how we've been doing routing on the internet since forever, so it's still deployed everywhere. Just a little bit of background here on BGP. The idea of routing on a graph, everything we've studied with distance vector and link state, the fundamentals of that were rooted in computer science a long time ago, long before the internet. Right? Things like Dijkstra's and Bellman Ford. This idea of how you route between autonomous nodes that have business policies just never existed before the internet. And in fact, the first 10 years of the internet, it did not exist. The internet was one flat, government-run network. No one worried about these things. So the development of BGP actually came fairly, late in the sense that it followed the development of the internet. And BGP was starting to be specified and deployed roughly at the time when the US government said, we are no longer running the internet, and handed it over to commercial entities. So it was a little bit of a learn as you go and build as you go. So because of that, as you'll see, BGP is not a perfect protocol. There are certain things that I think if we got to wipe the slate clean, we would do differently, and we'll talk about those. But on the other hand, it's proven effective. Right? You'll see lots of research papers that talk about here's the better way to do BGP. Invariably, when you poke at them, they seem to do like about 40% of what BGP does. So, they're simpler than BGP, but they're not really as general or powerful. Or they do, by the time they do everything BGP does, they tend to be not that simple anymore. So BGP is this thing we all, in the research community, we love to try and beat BGP, but it's proven to be a pretty difficult goal. Let's take a 2-minute break, and then we'll actually get into how interdomain routing works. Okay, let's actually design interdomain routing now. So a quick recap of our setup here is we have a graph. Nodes in the graph are ASs. Destinations are IP prefixes, and links represent both physical links and business relationships. And we've talked about what kinds of parts we like. There's kind of routing follows money kind of parts and so on. Let's talk about how we actually implement that. Right? And so when we think of how we're going to design interdomain routing, we've learned already, we have these two canonical approaches to routing that we've discussed, right? Link state and distance vector. If you had to choose one as your starting point, it's not going to solve all the problems we need. But if you had to pick a starting point, which would you pick? And why? Yep. Yeah, exactly. We would pick distance vector, and the reason is we don't like link state because link state offers no privacy. You have to broadcast your neighbor information to the entire graph. Right? And we said ASs don't want to reveal their business relationships. Even worse, it offers no autonomy. The only way link state works is because we all agreed on what metric we're optimizing. For that, I have to reveal my policies to everyone so that they can say, oh, this is how this AS would pick paths. Otherwise, link state doesn't work. So distance vector is a more attractive starting point. Right? The problem is it wasn't designed to implement policy. It was also doing least cost routing. The hook that we're going to exploit in distance vector to make it do what we want is the fact that distance vector is working by advertising per destination costs or per destination path selection. Right? And so that's going to be our hook. It'll make it clearer in a minute, but it's going to be our hook because it's going to allow us to say, on a per destination basis, I'm going to hear advertisements from other ASs, and on a per destination basis, I'm going to implement some kind of policy in which routes I pick. And I do it locally, I don't have to reveal it to everyone. That sounded big. We'll get to how that makes sense in a bit. So BGP extends distance vector in order to accommodate policy. The way we're going to talk about how BGP works, because BGP gets very detailed very quickly, so instead we're going to talk about going from distance vector to BGP at kind of an approach level and how policy is implemented. And then next lecture, we're actually going to get into the details of BGP messages and so on. But at this point, we're still in the general approach. So the basic idea behind BGP, if you remember distance vector, what was the basic idea? I tell all my neighbors about my least cost path to every destination. Right? So for each destination, I say, this is my least cost path. And then I listen to what my neighbors tell me, and I pick the best route to every destination based on what I hear. And we iterate between those two. We're going to do the same exactly for BGP. So in BGP, we're going to say that an AS, so now a node is an AS, advertises its best route to a prefix. We call this export. This is BGP terminology for advertising. So an AS will export its best routes to all its neighboring ASs. And at the same time, each AS is going to listen to all the advertisements it received, and it's going to select what it thinks is the best route for each advertised prefix. And we're going to go back and forth between those two. This should sound very familiar to you. This is what distance vector did. The change is that policy is going to be implemented in terms of which routes you advertise and which routes you select. Okay? So when we say BGP is inspired by distance vector, there are three similarities really. One is that we're doing these per destination advertisements. Destinations for BGP are prefixes. The second, there's no global sharing of network topology information. Instead, what we have is this iterative distributed convergence process. At no point am I telling everyone, these are my neighbors, these are my policies. That said, we're going to have to change distance vector, and there are four crucial differences. I think we've kind of touched on most, if not all of them, but let's repeat them so we make sure we're clear. The first is that BGP may aggregate destinations. So if you remember in distance vector, you got an advertisement that said, for this destination, here's my least cost. At no point did I mess with that destination, right? I just took that destination and I updated my least cost path and then I advertised it back out. I didn't tamper with what that destination was. In BGP, we do that. For example, AT&T in this context might hear advertisements from LBL, UCB, and UCSF. It's not just turning around and advertising those prefixes to Verizon. Instead, it's aggregating them into a shorter prefix and advertising that shorter prefix. Okay? So for scalability, BGP may actually aggregate routes and destinations for prefixes. That's one big difference. Does that make sense? Any questions on that, or anyone want me to repeat it? Okay. The second, we've touched on this again already, you're not necessarily picking shortest paths or least cost paths. Right? So BGP, you're going to select the best route based on this general policy that we said every AS can implement. and that policy is not optimizing some well-agreed upon cost. So it's perfectly reasonable in BGP to have a topology like this, where node 2 is going to say, I'm going to reach 1 by going through 3. Node 2 prefers the path 2, 3, 1 over 2, 1. That's totally fine in BGP. This should cause you concern. What's the immediate thing you think of when I tell you I can go 2, 3, 1 instead of 2, 2, 1? What's the thing we've been worrying about so much in distance vector? Loops, right? Least cost path routing had this beautiful property where I'm decrementing in this cost at every step, and so I don't get into loops. If I can't rely on that anymore, I could have loops anywhere. Right? So how do we actually avoid loops? Any ideas? Very different approach from all the things that, split horizon, poison rivers. Forget all about all those techniques. So there's something completely different you could do to avoid loops. Yeah, keep track of what that path is. And you should have this slight thought of why didn't distance vector do that? What BGP does is instead of doing distance vector routing, it does what we call path vector routing. Right? And so here, when you advertise, you also advertise the path, the entire AS level path to that destination. So for example, here when A advertises to B, it says I can reach this destination via the path A because you're the only AS. When B forwards that on to C, it says I can reach the destination along the path BA. So when C turns around, data goes from C to B to A, but if, sorry, my slides here are all messed up. The key idea, let me recap it. The key idea is you advertise the entire path. So the distance vector, in distance vector routing, we sent the distance metric per destination. In path vector, we're going to send the entire AS path associated with the destination. Again, so it's going to do what we did. And loop detection now is when C turns around and advertises to A, it's going to send an advertisement that looks like, I'm going to the destination along the path CBA. Right? So it's actually trivial for A to look at that advertisement and say, I'm on this path, this is a loop, and it throws that advertisement away. Right? So you're doing loop detection. Any questions on this? Great question. Aren't we revealing something about our policies when we do this? We are. But this is kind of the path of exposing your policies that's inevitable. What you are exposing is the path you've chosen. You're not exposing what paths you heard and which paths you rejected. So you're right that there is some leakage, but I would argue it's almost fundamental that you have to reveal this. Any other questions? Right. So just to recap, the key idea, advertise the entire path, different from distance vector. The benefits, loop avoidance is easy. There's another benefit that we don't really know how often this gets used, but it is certainly possible, is that you can look at the entire path and base your policies on the entire path, not just your next hop, or not just your cost. So you could say, oh, this path is going through some country you don't like along the way, and so I'm not going to pick it. That's actually something you can do with BGP. And the last difference between BGP and distance vector is what we call selective route advertisement. So in distance vector, the way we've been talking about it all along, we've been saying I receive an advertisement for a destination, I update my least cost, and I forward it on. You never had in distance vector a node that receives an advertisement to a destination and says, I don't like this destination, I'm not advertising it. That's not how the context we were operating in for intra-domain routing. But that's exactly what we're going to do with BGP. So in BGP, for policy reasons, an AS may choose not to advertise a destination. Right? So I can have a graph like this where B hears from A, and a route being advertised, and says, I'm not going to advertise it to C, because if you advertise it to C, you're going to be asked to carry traffic to that destination. And if B doesn't want to do it, they're just not going to advertise it. Do you see a problem with that then? Now that we're saying every AS can choose not to advertise certain destinations. Yeah? It just drops it. this should be a serious cause for concern, because what this is telling us is reachability is not guaranteed with BGP. Even if the graph is connected, that means I have links and I can draw this connected graph. Reachability is determined by whether all the right ASs along the way chose to advertise a path or chose to advertise that prefix. This should sound concerning, like how is the internet working? We'll get to in a few slides about why, in practice, most of the time, unless we're talking about bugs or misconfiguration, why this is not, in fact, a problem. So just to recap, the 4 differences: BGP can aggregate destinations and routes, which we didn't do in distance vector. Selection is not based on shortest path. You advertise the entire path, not just the least cost. So it's a path vector protocol. And you are selective about which prefixes you choose to advertise. Yeah? Right, so typically you lose some information when you aggregate, because what you would be telling Verizon is all of these prefixes routed through me, AT&T, and you kind of lose the subtle differences between the distance from AT&T to maybe LBL, UCB, and UCSF. You lose that. One could argue, that that was the only path to those prefixes in any case. So there's not, the downside is not that great. Any other questions? Yeah. Right, so I think the question is, in the multi-homing example we had, where we had a link from LBL to Verizon, and we said Verizon has 2 entries in its forwarding table. One is for a /8 for A, and the other one would be a /16 for A.B. And so how would Verizon choose how to send traffic between those 2? Is that the... Right. Mm-hmm. Verizon is not losing any of its own range, you're saying? Yes, so in that example that we had set up, the multi-homing example, that particular one, Verizon was not using its own range for LBL. Both ways, you could do it both ways. It really depends on whether you want 2 paths coming in for one given prefix versus having 2 different prefixes. LBL could have also taken a prefix from Verizon. It's just a question of what you were trying to achieve with the multi-homing. And in this context where LBL is asking Verizon to kind of accept its route to A.B, that's part of their agreement. Part of what they're signing up for is you will advertise my prefix for me as a provider. So it's a done thing. Any other questions? Okay. Moving on, any questions before on how BGP is like and unlike distance vector? Okay, so now let's talk about how policy is actually implemented in this context. And so remember we said we have this usual iteration of I export certain routes and then I listen to what everyone's advertising and I import or I select certain routes. Let's actually look at that a little bit in action. Because policy, or everything we've been talking about, all these concerns about how money flows and so on, where it actually comes down to where it gets implemented is this question of what routes am I going to import or select, and what routes am I going to export or advertise. So that's where, if you look at the implementation, that's where policy lives. Right, so let's look at this example here where I have these ASs, and I have some destination prefix somewhere far out on the internet, 128.3 dot something. And I have two paths, both B and C, have the ability to reach that destination. So I have this green path and I have the blue path. Both of them are advertising these paths to A. Right? So A is listening, it hears two routes being advertised, two paths being advertised for the same prefix. It's going to pick one. Okay, that is our selection policy or route import step. And that's the step where we're going to inject some amount of policy. Okay. In picking that policy, when I pick which one of these I'm going to take, what I am effectively determining is how my traffic is going to leave my network when it goes to that destination. Okay. So here, let's say that A said, I actually like the green path. So I'm going to choose the green path. What that means is that when I route, when A is given traffic or it carries traffic for 128.3 dot something, it is going to send traffic to B. Okay, so keep that in your head because remember we said when we send traffic, we like to make or save money. So keep that in mind. But now again, when I take that, I've selected that green path, that was my import policy. I have another step of policy, which is now whom am I going to advertise that path to? And again, remember, when I advertise the path, what I'm telling the person I'm advertising it to is you can send me traffic. I will carry traffic for this destination. Right? And again, remember, we said I only want to carry if I'm going to make money by doing so. So in this case, let's say that A decided it didn't want to advertise it to Q, and it did want to advertise it to P. So again, this export step of deciding where you advertise your paths, that's another place where we put policy. Okay, so policy is imposed in how routes are imported and exported. I'm going to repeat this again, a few times because it's intuitive, but we trip on it multiple times. So import determines which path I'm going to use. Your import policy dictates how traffic leaves your network. Your export policy, which is the question of which paths do I advertise, it controls how traffic enters your network. One last time. Import policies, which paths should I use or which paths should I accept, determines where traffic goes. Okay? Because you're choosing the route. Export policy, which is the decision about which paths do I advertise and where do I advertise them, determines what traffic enters your network or what traffic you're going to carry. Any questions on this? I've found it's easy to get confused because the import and export is kind of the opposite direction of traffic flow. So when deciding what to import, you have to decide what you're effectively deciding is where your traffic will get sent. And then you think about how the money flows. Okay, so we're going to have these import and export policies, and we've talked so far about, you have these business relationships and you have these principles around when you send traffic and receive traffic, where does the money flow and so on. All of that understanding or the language we use for that comes from work done by Alishan Gao and Jen Rexford. They were both researchers at AT&T Labs when they did this work. So it was in the early days of the internet where all the ASs were kind of just setting up their networks in some ad hoc way, and nobody quite knew what they were doing. So they went out and actually surveyed a bunch of these ASs and tried to understand what was in the heads of these network operators, what they were doing informally. And what they distilled from that are what we call the Gao-Rexford rules. These are rules that capture common, so they're actually, despite the name, not rules. They're not, you don't have to follow them, but it's common practice in import and export policies. Okay. And basically, they codify or show us the pattern behind this routing follows money intuition that we've had. So far we've been saying routing follows money. It's all been very intuitive. The Gao-Rexford rules translate that intuition into import and export policies. They're also very useful because, we've been saying so far, I'm not sure it's reachable. Different ASs can choose different policies. The Gao-Rexford rules tell us if every AS on the internet follows these rules, we can start to reason more formally about things like convergence, about things like reachability, and so on. So it's the closest we have to a more formal, rigorous baseline for interdomain routing. Which doesn't mean that an AS cannot go do some crazy thing. They can, but at least this gives us a baseline that makes sense. And as far as we know, all ASs follow the Gao-Rexford rules. So with that, what is the Gao-Rexford rule? This is, again, repeating that intuition. This says when I hear routes being advertised to me, when I select them or when I import them, the rule I'm going to follow is I will always prefer a route that was advertised to me by a customer over a route advertised by a peer, and the peer over a route advertised by a provider. This directly follows the when you send traffic, you either try to make or save money. Right? If you're trying to make money, you would always like your customer route. If you're trying to save it, then you'd prefer peer over provider. And only when you have no choice will you choose your provider. In practice, ASs will use additional rules. So, you might have, for example, many peers. Let's say you had no customers, but you had many peers whose route you could have picked. So typically what an AS will do is they will apply the Gow-Rexford rule. And they'll say, okay, I heard the path advertised from these 3 peers. And then they'll have additional policies for how to pick amongst those 3. And they'll do things like picking based on the performance of the path or, maximizing use of your network bandwidth and so on. And when we get to the details of BGP, we'll talk about how they implement those. But the Gow-Rexford rule is typically the first rule you apply. Similarly, Gow-Rexford on the export side. The question again here was now I have routes for certain that I've selected for certain prefixes. Where and whom do I export them to? And so remember here, again, when I export a route, what it means is that I'm accepting to carry traffic to that destination. So what is the policy we're going to follow? So what the Gow-Rexford rule tells us is it comes down to this table. And the question we're going to look at again is I'm going to export that route, which means I'm going to be asked to carry traffic to that destination. And we said I only carry traffic if I get paid for it. How do you decide whether you get paid for it? Right? The way you decide whether you get paid for it is you look at who advertised that route to you. Because that's going to be when you carry traffic, you're going to carry traffic to the person that advertised the route to you. Okay, so let's look at what those options mean. Let's say that you're a router here, we're the one in the middle, and I have a provider A, a peer B, and 2 customers C and D. Okay. Now let's say I had a path that was advertised, a prefix that was advertised to me by a customer. So let's say in this case that C advertised a prefix to me. And now my decision as my export policy, and remember, I'm only going to carry if I get paid, is that I will, whom would I export this prefix to? For example, so the question here is again, route being advertised by C to me, should I export that route to D? Yes, right? Because I'm going to get paid. Actually, I'm going to get paid by both C and D, so great. Should I export that route to A? Think about that. I see some people saying yes, some people saying no. Yes, because let's say I took that route from C and I advertised it up to A. So when I get traffic coming back from A to C, I'm getting paid to carry that traffic. Right? C is paying me. It is true that I'm also paying A, but that is actually also the nature of being a provider. But the requirement that I will only carry traffic if I'm getting paid, that is being met. Should I advertise that prefix to B? Yeah. No? Oh, some. I got a shrug and a yes. Yeah. You would export to all of them because otherwise you have no guarantee that C is actually reachable by everyone on the internet. Because what if B was only connected to one, X here and is not connected to some other part of the internet? In fact, you definitely should because let's say that B has some customer X here, but above B, B's provider is is Y, let's say. B is never going to accept to take traffic from Y, send it to me, and go down to C. Because that's going to be, B would get charged, B would not get paid. So in fact, you can't rely on B to connect you to the rest of the internet. You have to advertise it to A. That's a good question. Yeah? You will definitely get paid. So if I advertise C's route to A, and A sends me traffic to C, I will definitely get paid for it by C. There's a question about, do I end up getting paid more by C than I pay A? And that's kind of a market dynamics thing. The assumption generally is you figured out how this makes sense for you in terms of how the net money ends up being. And that if you as an AS are paying A more than you're being paid by your customers, you've probably not set up your relationships very well. Yes. Yeah. And the typical context here is, think of this as Berkeley and then let's say a California AS and then AT&T. If this California AS said, I'm not advertising Berkeley's route to the rest of the internet, then Berkeley's in trouble, right? So what this means is if my prefix was advertised to me by a customer, I'm going to export it to everyone. And I'm fine doing that because my customer is paying me to carry that traffic. Everyone happy with this? What if that destination was advertised to you by a peer? So now let's say that B had advertised a destination prefix to me. And the question again is, whom should I export this route to? And again, when I export a route, that means I'm willing to carry traffic to that destination. Customers. What about if I had a route advertised to me by a provider? Also customers? Why? Right. So if my provider advertises a prefix to me, that means that I will carry traffic to that destination from C or D, which is fine. Right? And this is, in fact, exactly what we want. Let's say, Facebook was somewhere out there in the world. My customers want to be able to get to it. And they're going to pay me for it, so I'm fine with this setup. Any questions about this? Understanding this is key, so if you have any lingering questions about this. Going once? So I said that the GAO-Export rules are nice because they give us a certain baseline that we can make certain statements about how internet routing works under the assumption that everyone follows GAO-Export rules. It's also kind of hard to see why someone would not follow GAO-Export rules. When you look at kind of the history of outages on the internet, they tend to be because someone misconfigured their policy, and so they were actually violating GAO-Export rules when they didn't mean to. So things like Berkeley by accident advertised a route to Google to AT&T, and suddenly all of Google's traffic comes through Berkeley. They tend to be mistakes. If you actually configured your policies correctly, typically everyone follows the GAO-Export rules. But so one of the properties we can talk about if everyone's following the GAO-Export rule is that all paths on the interdomain graph or on the AS graph are what we call valley-free routes. And again, we've covered this intuition, but what it's saying is if I took a graph where customer-provider links are going up in the graph and peers are going sideways, exactly what we've been talking about, then I will never have, or I'll always have paths that are valley-free. There's a kind of proof sketch that you'll see in the discussion section, but it's very intuitive. Why would you have a valley? You'd have a valley if you went down to a customer and went back up. We said we don't like that. It doesn't make sense. GAO-Export prevents that. Or you would have this kind of valley if you went to a peer and then went back up, which means you're going over a free peering link and then going up over a link that you have to pay for. Again, GAO-Export rules prevent that, so we don't see that. Okay, so all paths on this AS graph are what we call valley-free paths. There's a question? Yeah. Yes, exactly. So the path, actually that's a well put, the path you end up with is a combination of every AS node on the graph enforcing that import and export policy. So when I export a path to you, you can choose not to import it, not select it. That means I won't get traffic from you. But when I export it, what I'm saying is I'm willing to carry traffic. Whether you then choose to exercise my offer is your choice. Does that make sense? So I export it. All that I'm doing when I export is I'm saying I'm willing to carry traffic to this destination. If some AS chooses not to send me, not to pick my path, the only way I would see that is I wouldn't get traffic to that destination from that AS. But there isn't an explicit, no thank you, keep your path. Any other questions? Okay, so the last point to make about the Gao-Rexford rule is what the Gao-Rexford rule allows us to state is actually a fairly powerful statement about interdomain routing, which is that under two assumptions about the AS graph, which I'll get to in a minute, if all ASs follow the Gao-Rexford rule and these Gao-Rexford policies, then we're guaranteed two properties, reachability and convergence. Reachability means any two ASs on the internet are guaranteed to have a path. They can communicate. And convergence meaning all routers will agree on that path. So all these things we said about, each AS gets to implement their own policy, I can choose not to advertise a destination and so on. What this tells us is if you follow the Gao-Rexford rules, and under these two assumptions, which I'll get to in a minute, then we actually can make these, we're reassured. We can make these pretty strong claims about reachability on the internet. And so what are those two assumptions? They're actually key. The two assumptions are, one is that the graph of customer-provider relationships is acyclic. There are no cycles. That means I'll never have a situation where A is a customer of B, and B is a customer of C, and then C is again a customer of A. And if you think about what the implications of customer-provider are in the real world, that makes complete sense. Right? This would be saying Berkeley is a customer of Sonic, and Sonic is a customer of AT&T, and now AT&T is a customer of Berkeley. That should not make sense. So, but if this assumption holds, which we would always expect it to, that's one assumption underlying the Gao-Rexford conclusion. The other is that starting from any AS, you can always follow a chain of customer-provider paths up to a tier 1 AS. Okay, so I can start from any stub AS in the world, and if I kept walking up the customer-provider path, I will hit a tier 1 AS. And then remember the tier 1 ASs are all peering with each other. So this should tell you why these two assumptions are key, because the assumption that you have no cycles is what allows us to draw this conclusion about convergence, that we will all settle, you won't oscillate in a loop. The assumption that we will eventually reach a tier 1 is what guarantees reachability, because this means you can always find a path where I walk from my stub AS up to a tier 1, and then the tier 1 will jump across a peering link to a tier 1 AS connected to the destination, and then we'll walk back down the hierarchy to the stub AS on the destination side. Okay, and again, in section, you'll go through the arguments behind those claims a little bit more. What is important to realize is neither reachability nor convergence are guaranteed if we are in the space of more general policies. There's actually been more formal theoretical work showing that if you have, deviate from something like the Gao-Rexford rules or these assumptions even a little bit, then all bets are off in terms of what you can say about convergence or reachability on the internet. And you'll do an example in section where you'll see how routes can oscillate forever and never converge if you're not limited to the Gao-Rexford rules. So with that, just quick recap. Policy is implemented by choosing which routes you import and which routes you export. The Gao-Rexford rules tell us, kind of common sense practice about which routes to import or export in order to make or save money. And that's the underlying principle is this is driven by how the money is flowing between these ASs. And if we all follow the Gao-Rexford rules, kind of good stuff happens on the internet. We can rely on the internet to actually provide universal reachability. Any questions? No? Okay, so next lecture we'll get into the protocol detailed weeds of BGP and also move on to the data plane. Thank you.